In this video, I'm going to be making ethane gas to use in the second stage of a cascade refrigeration system. This video is sponsored by Squarespace. Now I know what you're thinking, didn't I already do this a couple months ago? Nope, that was ethylene, also known as ethene, which is C2H4. Here, I'm going to be making ethane, which is C2H6. This is ethylene's fatter cousin. So what's even the difference and why bother? Well, see, the ethylene I made in the past is a very, very low temperature refrigerant. At atmospheric pressure, it boils at minus 104 C. This is great for a system bordering on cryogenic temperatures, but there's a major catch. It requires a lot of pressure to condense it. Even as far down as minus 20 C, you'd need about 25 bar or 350 psi in a heat exchanger for condensation to occur. Now, for a beefy rotary compressor made to handle pressures in excess of 30 bar, that's no big deal. But when I did my video series on cascade refrigeration, I was using tiny little compressors from tabletop ice makers which didn't like to go much above 100 to 150 psi or 8 to 11 bar. And if you watch those videos, you may recall that getting my ethylene to condense was extremely difficult because of the pressure needed. However, I was able to condense CO2 or nitrous oxide with my weak setup. My heat exchanger temperature was about minus 20 C. At that temperature, CO2 requires 19.7 bar or 271 psi to condense, and when sublimation occurs at 1 atmosphere, it drops to minus 79 C. Nitrous oxide requires just 14 bar or 189 psi and drops to minus 88 C at 1 atmosphere. The problem is, CO2 will freeze and clog the pipes if it drops below its triple point of minus 56 C, and nitrous mixed with refrigerant oil is asking for an explosive disaster. However, there's another option that's not a synthetic refrigerant, which is ethane or R170. At minus 20 C, ethane requires only 14.2 bar or 191 psi to condense and drops to minus 89 C at 1 atmosphere. In fact, its pressure versus temperature curve almost exactly matches R508B, which is a common synthetic refrigerant used for industrial cascade systems. It'd be much easier to get this to work in a mini cascade system than ethylene. The tricky part is making it. Now, the first way involves a hydrogenation reaction where ethylene gas and hydrogen are fed into a hot chamber with a catalyst metal, which I think is ultra finely powdered nickel. The ethylene reacts with the hydrogen, breaking the carbon double bond and squeezing in 2 more hydrogen atoms, forming ethane. The problem with this method is you'd still need an apparatus for making ethylene and a hydrogen generator and a bunch of ultra finely powdered nickel, which I've heard is very dangerous to work with. So yeah, I don't think I'm going to do that. The other way is through electrolysis. Now you may be wondering how the hell you get a hydrocarbon molecule from electrolysis, and to be honest, I'm still wondering the same thing, but it does work. So usually when you pass a current through some aqueous solution, you get hydrogen on the cathode and oxygen on the anode. Sometimes you can get other weird stuff too, depending on the pH and the electrolyte substance, like chlorine on the anode from saltwater electrolysis or CO2 from using baking soda as an electrolyte. But if you use just platinum as an anode material and sodium acetate as an electrolyte instead of just splitting the water molecules, it'll start splitting acetate ions in a process known as Kolb electrolysis. Under the hood, there's actually some really complicated organic chemistry stuff going on here, but here's the inputs and outputs. If you take 2 moles of acetate ions, the anode oxidizes them to 2 moles of CO2 and 1 mole of ethane, and 2 moles of electrons. That 2 moles of electrons part is important, by the way, because we can use that to calculate the theoretical yield based on the input current. By knowing that 1 amp is 1 coulomb per second of charge, taking the charge of an electron and Avogadro's number, which is the number of particles in a mole, we can figure out that 1 amp should give 0.019 moles per hour of ethane, which is about 0.44 liters per hour. The only problem is 2/3 of the output is CO2, which is a bit of a nuisance, so we'll have to remove that with a scrubber to extract the pure ethane, which I'll show later. Now, if all I need is acetate ions, why not just use straight acetic acid, aka vinegar, instead of sodium acetate? Well, I could, but the electrical conductivity of vinegar is really low, so using some sort of acetate salt works a lot better. Sodium acetate is really easy to make. In fact, you've probably done it before if you've ever made one of those middle school science fair volcano things. When baking soda reacts with vinegar, it gives off CO2, which you're probably familiar with, but what's left behind in the solution is sodium acetate, assuming you had a balanced reaction. It's pretty safe to work with, and when I accidentally drank some, I discovered that it kinda tastes like pickle juice. Now, using pure sodium acetate won't do us much good in the long run, since the acetate ions are consumed in the electrolysis reaction. If the cell is left running long enough, all that sodium acetate will get converted to sodium carbonate and then sodium hydroxide. Then, not only will we not be having ethane produced on the anode anymore, but instead we'll be making oxygen and mixing it with ethane that was originally being produced, making, a bomb. So to avoid that, the sodium acetate is in a healthy excess of vinegar so that as the acetate ions are consumed off the sodium acetate, the lonely sodium goes and grabs another one from the acetic acid. At least that's how I think this all works. I really have no idea what the hell I'm doing, to be honest. Let's start by making the electrolyte. I'll mix up 330 grams of baking soda and 600 milliliters of water. That's not enough to dissolve it all, but as long as it's getting mixed around, it should react when I pour in the vinegar. Then I add 750 milliliters of 45% vinegar. I only add a tiny bit at a time, otherwise the foaming from the CO2 that's produced will cause the solution to overflow. You can use sodium hydroxide instead of baking soda to avoid the foaming since that reaction doesn't produce gases, but I really hate working with it because it's so caustic. Okay, so in theory I've got 3.93 moles of sodium bicarbonate and 5.63 moles of acetic acid, which should give me 3.93 moles of sodium acetate and then leave an excess 1.7 moles of acetic acid. Once the reaction is finished, I add a little distilled water so that the total solution volume is 2 liters. This gives us a pH of 5.6 compared to the 2.2 for the 45% vinegar, so it's pretty close to being neutral. As we'll see later, that didn't end up being quite enough excess of vinegar to work well. Also, as a side note, there's this weird oil stuff that floats on the surface of the solution. Even after attempting to filter it out, there's still some left over and I don't have a clue what it is. If you recognize this, let me know in the comments because I'm curious to know what it is. Okay, now it's time to build the cell. This one is going to follow the same design as my automated hydrogen generator, but at about half the size. I'll have a glass bell that collects the anode gas. As the gas accumulates, it pushes down the water line in the bell, which causes the water line outside the bell to rise. Once the outer water line goes above a certain point, a sensor turns on a pump that sucks the gas out through a tube with a check valve. First, we need the electrodes. The cathode will just be some scrap copper tubing I had laying around, but the anode is much more important because it has to be platinum. See this tiny piece of wire? This cost me $80, and that's because it's pure platinum. I actually measured it with calipers and weighed it on a milligram scale to determine the density, and I did verify that it is actually genuine platinum. The platinum anode is soldered to some ordinary insulated copper wire, but I'm concerned about what nasty chemical reactions might occur at this joint, so I placed a little ABS block over it, then used a slurry of ABS scraps dissolved in acetone to cover up the joint and seal it off. Both electrodes will be mounted concentric to each other on this ABS ring with the glass bell between them. I used my ABS putty again, this time to secure the electrodes because I wasn't sure if regular glue would hold up to the harsh chemical environment. Once the anode is in place, the cathode is inserted and also tacked down with some ABS putty. Then I constructed a suction tube for the anode gases with some more ABS parts. Here's how it looks with the glass bell over it. But unfortunately, the ABS tube was porous and leaked, so I had to use glass instead. This was a pretty good opportunity to try some glass forming, which I'd never done before. Fortunately, it's pretty easy to do with borosilicate and MAP gas. I just took a 12mm tube, heated it up for a minute, and bent two 90-degree angles in it. Pretty straightforward, you just have to remember to let it cool very slowly so that it doesn't crack. The outer tank of the cell is just a glass bowl with a plastic lid, which I cut with a hot knife for the glass bell and made some additional holes for a tube feed-through, electrode feed-through, fill port, and electrical probes to detect the water level. The probes are two stainless steel screws. They have no problem triggering when they're contacted with metal or quickly shoved into the electrolyte, but when the water level moves up slowly, even when they're submerged, they fail to make electrical contact. I suspect this is related to that weird oil stuff I mentioned earlier. My guess is that if the water level moves up slowly enough, the surface tension somehow causes the oil to form some sort of envelope or membrane around the electrodes so that they can't conduct electricity. This problem was fixed by just replacing the electrical probes with a float switch. Which leads me to the electronics controlling the system. Now, in my hydrogen generator, I used an Arduino to manage all the logic of turning on the pump, the compressor, the electrodes, etc. But using an Arduino for that is like using a chainsaw to do a job that kid scissors could do. There's way more computing power than I need for this project. So I decided to make my own analog circuit to control the whole system just to see if I could do it. I just gotta run down to Radio Shack and buy a few transistors and op amps. But what's this? My piggy bank is empty. Oh no. That can only mean one thing. Let me tell you about a little thing called Squarespace. Do you have a business idea? Well, in 2024, you'll need to use that World Wide Web thing to get anywhere with it, and that means having a website. Whether your business involves selling homemade teddy bears, offering marriage counseling in your garage, performing exorcisms, providing engineering consulting, or you're an artist trying to feature your portfolio, you're going to need a public-facing website to do business. That means finding a reliable host, a lot of coding knowledge, secure payment processing, search engine optimization, some way to track user metrics, and a reasonably professional level of graphic design, unless you want to look like you're stuck in the 90s. Squarespace has all those angles covered, so you can quickly and easily set up your website and impress all your friends by telling them what a cool entrepreneur you are. Go to squarespace.com for a free trial, and if you want to launch a website, go to squarespace.com/hyperspacepirate to save 10% on your first purchase of a website or domain. Okay, back to the circuit. Let's start with the current control. I wanted to have a constant current power supply to the electrodes rather than constant voltage. By having a fixed current, I know theoretically how much gas should be produced, and I can compare that to the actual yield to determine the chemical efficiency. The electrical efficiency will suck, but I don't really care about that. To do this, I used an LM317 linear regulator as a constant current source by providing it feedback through a 1.8 ohm resistor, which should theoretically provide 700 milliamps of current based on this formula. The LM317 output goes to some terminal blocks for the cell electrodes, and if this MOSFET is on, then current flows to ground and the cell is running. The other important piece of hardware is the pump that extracts the gas from the glass bell. That's also connected by some terminal blocks and turned on by this MOSFET here. Now both of these things require a little bit of logic to control, and it all depends on this, the water level sensor. When the water level sensor isn't tripped, i.e. it's open circuit, both of these op-amps have their outputs low, meaning all these transistors are off and the MOSFET controlling the cell current is on because its gate is pulled up by this resistor. In other words, business as usual, and the circuit effectively looks like this. When the water level sensor trips, it closes this circuit and starts charging up the capacitors on the positive rails of these op-amps through these 100K resistors. When the voltage on the positive rail exceeds the voltage on the negative rail, which is a fixed 6 volts, the op-amp turns on. This happens after about 0.7 seconds on the first op-amp. When it goes high, it turns on the MOSFET that controls the gas pump and sucks the excess gas out of the glass bell. This causes the water level outside the bell to fall, and when it falls far enough, it turns off the water level sensor again. Then, the capacitor on the positive rail of the op-amp discharges through this 1 mega ohm pull-down resistor, and the whole thing shuts off after a few seconds. The reason it has these built-in delays is to avoid jittering if the water level sensor is just barely straddling the trip point. After that, it's back to business as usual. But what if something goes wrong, and the pump stops working and the water level keeps rising? That's what the second op-amp is for. It doesn't turn on until the water level sensor has been tripped for over 3 seconds, hence the larger capacitor on the positive rail. If the water level sensor is tripped for this long, my assumption is that something has gone wrong and the whole system needs to be shut off to avoid having the electrolyte overflow from the bowl. So when the second op-amp turns on, the first thing it does is feed voltage back onto its own positive rail through this diode. This serves as a latch so that it turns on and stays on no matter what, basically a panic mode which persists until power has been completely removed from the circuit. It also turns on these 3 transistors. One pulls down the gate of the pump MOSFET, one pulls down the gate of the cell MOSFET, and one turns on a transistor to illuminate this LED indicating the system is in a panic mode. Because the cell will need to run for days on end without supervision, this is my way of ensuring I don't wind up with a bench in the garage covered in vinegar. There's one other little detail I need to mention about the electronics. The float valve is normally closed, i.e. it's conducting when it's in the fully down position, which is the exact opposite of what I wanted. To fix this, I had to make a logic inverter with 2 resistors and an NPN transistor. All this does is pull down the transistor base when the switch is closed and allow the resistor to pull it up when the switch is open, allowing it to supply current to the op-amps in the logic circuit. Okay, let's put it all together. Here's the cell going onto a little wooden board, and here's the control circuit mounted on an ABS bracket. Next, I place a bracket for the pump, and then the pump itself. Here's a look at the float valve. At 12 volts is pulling 0.7 amps exactly as intended. Right away, bubbles are formed, which means it's working. I mark out different points on the glass bell at different times to get some idea of the gas production rate. Okay, so 2 moles of acetate ions create 1 mole of ethane and 2 moles of CO2, which is 36 liters of gas at 25 C. Of course, that's courtesy of these 2 moles of electrons. Now, 2 moles of electrons translates to 193,000 coulombs of charge. An amp is 1 coulomb per second, so that's 53.5 amp hours for 72 liters of gas. That means 1 amp gets us 1.35 liters per hour of gas, so the 700 milliamps in my cell should give me about 0.94 liters per hour if there's no losses or leaks whatsoever. Now, the actual ethane portion is 1/3 of that, or 0.31 liters per hour, which is pretty tiny, but if this thing was left running 24/7, that's 52 liters of ethane in a week, and 104 liters in 2 weeks, which is probably enough to fill a small refrigeration system. Now, obviously, the CO2 will have to be removed, but I'll get to that later. Okay, so I'm all set up now, and I've got my beach ball attached to the gas pump, so let's run the cell and see what happens. I did some time lapses so you can see the water level going up and down as the gas is generated and then pumped out. Here's what I've got after 24 hours. The beach ball is about 26 liters fully inflated, and this is less than half inflated, meaning that the average production rate was around half a liter per hour, which is just a little more than half of the 0.94 that I originally predicted. And here's the 48 hours of running. I'd estimate the ball is about 3/4 full, which would be about 19.5 liters or 0.4 liters per hour. This seems like it's way less than it should be. Let's test a sample of it to see if it burns. Yep, that's gotta be ethane, because if it was oxygen, the bubbles wouldn't burn. It's also definitely not hydrogen, because it has such a slow, lazy burn, whereas hydrogen goes off really quickly even if it's not mixed with oxygen. It also burns straight from a syringe. Okay, let's get back to making more gas. And here's what it looks like after another 48 hours. Barely any gas went into the beach ball, so what the hell is going on here? Well, remember how I said earlier that I didn't have enough excess vinegar? Well, this is the result. As you can see, the pH is now showing 9.6, meaning the solution has become basic. This is because as the acetate ions got consumed, the sodium acetate turned into sodium carbonate, or bicarbonate, I get them mixed up. Either way, they made the solution alkaline, and now instead of creating ethane and CO2 on the anode, the cell is creating oxygen. Now if we look at the equation for water electrolysis, it takes a whopping 4 moles of electrons to make 1 mole of O2 gas. Our theoretical yield for the ethane-CO2 mix was 0.94 liters per hour, but for the O2 gas, it's 0.16 liters per hour, so it's no wonder the ball is barely full after 48 hours. I quickly rectified this by pouring a generous amount of 45% vinegar into the cell, and you can see the dramatic bubbling that occurs as CO2 gas is released from the sodium carbonate, or bicarbonate, or whatever it is. This brought the cell back down to its original pH of 5.6, but I feel like that's too close to being neutral, so I probably want to be somewhere between 3 to 4 just to make sure I have a really big excess of acetic acid. Another telltale sign that we've got sodium acetate again is the reappearance of that weird oily layer on top of the water, which had disappeared after several days. Also, the smell of vinegar is pretty noticeable now, which it should be. I also found a more accurate way to measure gas production rate, which was by connecting the pump output to a syringe, measuring the gas output at each turn-on, and then measuring the time between turn-ons. Using this method, I measured the new production rate to be over 1 liter per hour of gas, which was actually larger than the theoretical 0.94 that I calculated. However, these syringe markings have a decent amount of error, which probably accounts for the difference. After a couple days of collecting gas, I've got my sausage tank pumped up to 50 psi. The tank volume is 2.5 gallons or 9.5 liters, so I should have about 32 liters of gas above 1 atmosphere. This mix is 2/3 CO2, so I need to scrub that out to get the pure ethane. To do that, I made some calcium hydroxide, or slaked lime. You can buy this stuff pretty cheap, but I actually made mine for another project. It's pretty easy to make by just reacting calcium chloride with sodium hydroxide, aka road salt and lye. Now, having this in a fine powder wouldn't really allow gas to flow through it, so I've dried mine into these little chunks. These will leave lots of empty space between them for gas to flow through. The jar on the right is full of the calcium hydroxide pucks to scrub out the CO2, and the jar on the left is full of silica gel desiccant to remove the moisture in the gas, which it's definitely going to have since it came from electrolysis. In theory, the raw gas should go in the left side and pure ethane should come out the right side. Now, this might not catch all the moisture and CO2 in a single pass, but if that happens, then I'll just circulate the gas through these canisters until it's been completely cleaned. So I've got my tank hooked up to my dryer and scrubber with the output attached to a deflated beach ball. I'm going to just slightly crack the valve so that the gas has plenty of time to react with the scrubber contents. I could tell the CO2 scrubber was doing its job because it was getting very hot and condensation was occurring from the water vapor generated by the reaction. The beach ball was only partially filled after the first scrubber run, probably around 20 liters or so, whereas I had started with about 32, so I'll have to do a few more runs. I'll reverse the process by sucking the gases back into the tank through my refrigeration compressor, forcing them to travel through the scrubber once again. And after those 2 passes through the scrubber, the gas pressure in the tank is down to 30 psi from the original 50. Note that there weren't any leaks in the lines. After another 2 cycles, it's about 26 psi, and another 2 puts it between 24 and 25 psi, so I don't think there's much CO2 left to scrub out now. I spent 2 weeks generating and purifying more ethane gas with my tiny cell until I had over 100 liters in my tank, which was enough to try liquefying it. I hooked up my tank to my fridge compressor inlet, and the fridge compressor will discharge into the interstage heat exchanger I borrowed from my cryocooler. The interstage heat exchanger will get down to around -10 to -20 C, which will be cold enough to liquefy the ethane with some pressure. At the top of the heat exchanger, I've got the output hose of the compressor, and on the bottom, I've got a copper tube attached to a valve with a naked thermocouple directly in the discharge path. Oh yeah, this thermocouple back on top measures the heat exchanger temperature. The current ambient temperature is about 20 C, and the heat exchanger is sitting at -12.6 C. After pumping the entire tank into the heat exchanger, pressure is about 255 psi or 18.6 bar, which corresponds to a boiling point of -10 C on the ethane, which seems more or less right. Considering that I've pumped about 100 liters into a space that's only around 300 milliliters, I'm pretty sure it's all liquefied now. Let's open the valve and let her rip. And there you go. We went from about -10 C to -90 C. Now the boiling point is -89 C at 1 atmosphere, but it's not surprising to see a few degrees lower in the discharge stream because the high velocity gas would be at a lower than atmospheric pressure. So there you go. That's how to make ethane refrigerant. It's a little more complicated than ethylene, but not actually that bad. Also, my production rate was really tiny due to the tiny amount of platinum I had, which I didn't want to damage by putting too much current through it. But I think the pure platinum anode can be replaced with a larger platinum-plated titanium anode or a lead dioxide anode similar to what you might find in a chlorate cell. Assuming those options work, you could easily get orders of magnitude larger production rates than what I had in this video. You just have to make sure you're constantly monitoring the pH of the cell and adding vinegar to replace the acetate ions that got consumed. Personally, I still think I'd rather just use ethylene with higher pressure compressors, either in a cascade system or my Joule-Thomson cryocooler, but ethane is definitely a great option if you're trying to build a really tiny low pressure cascade system with small compressors, or replace refrigerant in a system that uses R508. Thanks for watching, and hopefully I'll see you next time.